del talk dell'altra volta che parlava di HBase. Poi abbiamo un ospite che viene direttamente da Monaco per farci la sua presentazione su Apache Spark e su come scrivere applicazioni Apache Spark. Partirà lui, si chiama Philip, e ovviamente il suo talk sarà in inglese, quindi dovrete impegnarvi un po' di più. So, can you present yourself and start whenever you want?
All right, thanks. Just one second. Need to reorganize that. Oh, it's good. Yeah, buonasera. Hi, my name is Philip. I'm from Munich, so I'm going to present in English. And I'm very glad being here in Bologna, that beautiful city, and be talking with you about writing scalable Spark applications, hopefully. I mean, scalable in terms, it's not just the only measure that we should take into account when it comes to performance of Spark applications, because there might be other factors that might play a role when we want to enhance the performance of our application. For example, I mean, it's not readable at all, I think, unfortunately, because that's actually, the web UI of a application of a client that I've been working with. So I'm a big data consultant. I have my clients to build big data applications. And here you see that the GC time, the garbage collection time, is red, and it's not only red, which means it's more than 10%. But in this particular case, it says the application has been running for 6 hours, and there were 5.8 or something garbage collection. Meaning that this application was indeed scalable because there were 8 cores running. It was just a simple machine, so it was parallelizable, but it wasn't performing. So unless you wanted to measure or monitor or stress test your garbage collector, right? So that wouldn't be that's what we wouldn't consider a performant collection application. So also at the same time, when I met them, there was a very interesting team structure. So they had basically 2 types of developers there. On the one hand, they had very experienced and very skilled software engineers that were capable of building very clean applications. On the other hand, they had very well. On the other hand, they're very skilled domain experts, in this case, mathematicians. And then I came in because they had problems scaling their application, so I came in as looking at the problem from a big data point of view. So we had 3 different types of developers looking at the same problem, and each of us trying to apply different principles on it, which was challenging at the beginning. But when we sat down to analyze that application, we found many problems. Some were pretty obvious, like this one. I mean, you look at one number, and it's always obvious looking at one number, and you can tell what's going wrong with your software. But sometimes, yes, you have to do some more sophisticated research. Yes. So the point that I'm trying to make is sometimes, or if it comes to performance debugging of big data applications on distributed systems, we need to understand what's going on internally, and we need to know some key concepts of the framework that we are using in order to derive the right conclusions. So even though Spark provides many very convenient to use and easy to learn high-level API like Spark SQL, which you can sit down and write 10 lines of code, and it will be executed on hundreds of nodes. Sometimes, once you face problems, you might be in help knowing something that's going on internal, and you can do your own debugging. And that's what this talk is actually going to be about. That's the most important reason that I think is important to why we should try to understand internals is really it's easy to collect numbers like this one, to see what's happening, like shuffle read bytes, shuffle write bytes, using Spark internal tools like metric system or REST API, but to draw the right conclusions, to ask the right questions to those numbers, to query the numbers in the right way, we need to know what's going on, and that's what we are trying to discover today. So at first we will look at the very basic, the most fundamental concept that Spark's been built on and its implementation, the first one, which is MapReduce, and secondly we will look at some Spark and core internals to hopefully give you a better understanding, if you don't have it yet, what's going on under the hood. So, yeah, as I said, the most fundamental concept of Apache Spark is data decomposition. And one implementation, also as I said, was implementation of MapReduce. And data decomposition in the end, it's just if we have a larger amount of data, we split it into smaller splits called partitions, and we execute some functionality on those partitions independently of all others. So we can look only at a subset of data and apply that function. But then, usually we want to query the whole data, not just the small piece of it. So we need to redistribute our intermediate result in order that we can execute another function independently of all others on that intermediate result, so that we have looked at the whole data, right? So as always, we apply a function, then we redistribute data in some way, which is of course dependent to the use case, to the application. So we have to specify how it's redistributed, and then we reapply a new function, which will again be independent of all others, and those we can just schedule where it's free. So that's how parallelism actually is achieved in Spark. So let's go and see how MapReduce actually implements this paradigm. So we also have a master. We have a huge data set which are the books. So you can think of this example as a word count example. So you have a library section of, I don't know, computer science, or I think it's animals here. And you want to look at all the books and build a word cloud, for example. So you want to count occurrences of nouns in all the books, right? So the master splits actually the data into m partitions, and m is specified by the user, of course. That's our partitions. Then we have 3 masters, and they're accessing those data. So they're fetching those data from the database, for example. And then they apply the map function on each of those atomic objects. Basically, they produce an intermediate result, which consists of a list of keys and values, which are different. It could be different keys and different values. Like here, for example, we have that word occurrences of nouns. So then we have that partitioning function, which specifies really how the data will be redistributed. I don't know if you can read it. So we have a transformation from a word, for example, to a partition ID. And this partition ID, so words that will be, same words will be hashed to the same, will be mapped to the same partition ID. So we use that transformation function to redistribute the data. So all data that hashes to the same partition will be fetched by the same reducer. And the reducer will actually apply this reduce function on all those data which will be hashed together. So there's a difference between a partition ID and a key, right? So there could be several keys could be hashed to the same partition. For example, here we have 4 different words, but we only have 3 buckets, so 2 words will be hashed to the same bucket. Now, each of the workers creates a file on the local file system, writing out this intermediate result in such a way that it is not only partitioned, but it's also sorted. Because a reducer will have to fetch the data from the map face, which this file is the map output file. So that's the shuffle B bytes. Right? It partitions this file such that the reducer can go and fetch only that data relevant for one reducer. And it's sorted by key, not by partition, because it will apply the reduce function iteratively on all those pairs. So if they were not sorted, they could be random occurring, and we could not apply that function iteratively. So all of our executors, so we report our, task state, so we let the master know once we are done. And we also report the location of the map output file to the master and tell him where he can find it, or reducers can find it. So all our workers do that. Now we're in the reduce phase. So again, there are workers who have that map output files on their disks. And now the master schedules reduce tasks, which are again independently executable functions to our workers. And also, the master assigns one partition ID to every worker. So for example, the leftmost worker here will reduce partition 0. And we've seen that partitioning function before, so it will fetch all the data which hashes to partition 0. So it goes ahead and fetches the partition 0, so all the orange data from the other executors, and apply that function. And what he also has to do, because he fetches sorted files, sorted by key, he gets 3 of them, so he has to merge them together such that it's sorted again. And it also, of course, uses that information that it has been sorted before. So that's a very smart sort algorithm called heap sort. So we have our data, and now we can apply a reduce function to each of the keys. All right. Same for the second executor, which has only one pair, and the third. And yes, so, and Spark at its core, it works exactly like this. It's the very same. But, did I miss something here? No. So, we don't write map and reduce functions for Spark, right? So we know that. So how is it done based on map reduce paradigm? In the end, Spark adds another abstraction to that paradigm and builds up on it. And adds very many enhancements over MapReduce because it adds another abstraction, like another programming model to that MapReduce paradigm by providing something that appears to us that being a distributed collection of objects called RDDs, resilient distributed data sets. And those RDDs, I don't think too much of them as being collections, but rather I see them as computational steps in a transformation chain, how we get from some input data to some transformation step. So RDDs basically that they define more abstract transformations, like you can think of them, they define transformations, and they are basically building blocks in a computational chain, which tells the cluster how to execute, or what to execute on the data to get to some specific point. And there are different implementations of RDDs, which basically are just specializations of those. They add some special properties, for example, a sorted RDD or a co-grouped RDD. So there are different implementations, but at its core, they are just definitions of transformations. RDDs are just defined having some special properties. At first, they only provide cross-current transformations, meaning that we cannot alter or change one single object within an RDD, but rather we can only apply some functionality to all of them at once. We only can apply all of them at once, right? Because it's just, when we call a transformation, it's just adding a step to the transformation chain. We cannot pick out one object. Then RDDs are partitioned the same way, meaning the same as in MapReduce. Having a partitioning function, which also specifies how data will be redistributed then in the end. And they are immutable, meaning that we always get a new RDD back once we transform one. Again, as it's only adding one step to a chain. And they track the lineage so they reference its parent and they tell how do we alter the parent in order to get to the next step. They're lazy, meaning that we need to call an action and so that they get materialized, and we can add flags to the chain that tells the cluster to persist in an RDD once it's materialized on the cluster. So I guess all of you know that already, and those are actually, this is the interface. This is actually the interface of an RDD, and that's all the information that the Spark execution model has for scheduling the execution of the transformation chain. So it's not too much, and it's pretty obvious. Like in the iterator function, that's actually where the computation happens, where we provide an iterator for the next parent of all of our objects. So if we build a user program, usually we start by creating a new RDD, and then we can transform it, which builds up a logical plan. For example, we have now a new transformation, and then we repartition it, which means we distribute data based on some partitioning function, as it was in MapReduce before, and we step by step with applying a new transformation, we add new RDDs and dependencies to this logical plan. Right? So we have a second one which will be mapped, and then we have a third one, and we're going to union them together. And what we see here is, for each transformation, there will be RDDs added to the logical plan. And there could be more, of course, there could be more RDDs than transformations that we call on that RDD. So now, all right, so this logical plan, it basically describes how we can derive any RDD that we can reference in our logical plan, how we can derive it from stable storage. But there's nothing happened yet. It's just a chain of transformations. And it consists of RDDs and dependencies and partitions. So the red circles, they are partitions. And the arrows, of course, are dependencies. And there are two types of dependencies in Spark. At first, we have narrow dependencies, which you can think of for now as one-to-one dependencies, meaning as we have put here in the RDD2 in the middle and in the top, each partition will be transformed simply into another partition. So there will be no data exchange. That's simply one map stage followed by a map stage in MapReduce paradigm. On a more formal way, an arrow dependency is defined as if a parent partition is used by at most one child partition. And we can understand that better why it's defined that way if we look at the contradiction of the definition. So if one parent partition is used by more than one, meaning two or more child partitions, that would mean, like in the lower shuffle dependency here, the leftmost partition is used by three child partitions. And that's not a narrow dependency because we could not apply three child tasks like the reduce functions. We could not apply it to the single partition in parallel without being independent of data. Right? So in order to schedule the three reduce tasks, the three child tasks, we would need to redistribute our data again, so that we can apply the function on the subsets of data completely in parallel on our cluster. So there are no interdependencies anymore. That's why we have all those errors here. So we have to redistribute data to different machines such that each reduce task can work independent of all others. All right. So on the execution model, now we have built this logical plan. How does Spark actually execute such a logical plan, which we specify in our user program, actually on a cluster? And basically, it uses some key components that I would like to mention here, because I think that those are really the key players of Spark. And once you stumble across them, you actually know what they're doing, and you can collect some metrics on them. So usually at first we create a Spark context, which actually sets up all the context, right? It instantiates everything, it sets up connections and stuff and configurations. And then we use this context to parallelize or to read some data from somewhere. It's always the Spark context who is the initial player here. So the Spark context returns us an RDD, the initial RDD, which we transform a couple of times, building up the logical plan, and then we call an action, which will actually trigger execution. And what happens then is the RDD knows the Spark context, and it will call a run job and passes itself, such that the context can use the DAG scheduler, which is a directly acyclic graph scheduler, who is responsible for the transformation for the execution. It's really the central component. It's event queue based, so it tells itself to submit a job, puts it to the event queue, and once it handles that handle job submitted event, it does two things. At first, it transforms the logical plan into a physical plan, and then it uses the physical plan to schedule tasks using the task scheduler, which can then talk to the cluster. So the task scheduler actually serializes tasks and sends them to the workers, and which will execute them and report back results to some other components. But on the first phase, we're going to stick to this ones. So how does the transformation of the logical plan to the physical plan happens? And that's where we really see that Spark is really based on MapReduce. So we are in the handle job submitted call, and we have that RDD, which is the logical plan. And it's basically, it looks like this. You probably know that picture. And what that DAG scheduler does now, it starts from the back, and it creates a new stage. So a physical plan doesn't consist of IDs and partitions anymore. It consists of stages and tasks. And what the first thing we do is we instantiate a new stage, we add a new stage, and then we go backwards, scanning the dependencies, the parents of each RDD, to see, to put together, to add them to the same stage once, if they have a narrow dependency to the child. So here we have only narrow dependencies, so we can pipeline all those map stages, one-to-one dependencies together. So oh no. So now we have created one stage, and now we have at each of the borders, each of the current dependencies of the border IDs, using the same algorithm. So we would scan back here also the dependencies and pipelining together all the narrow dependencies. And same we do on the top, in the lower stage. So here we pipeline together IDDs as well. Now we started from the very back, which is producing our result. So the last one is actually called a result stage, and all the other ones are shuffle map stages, because they are just used to create the final stage in this particular action. We do this for every action in our program, and then we start to commit those stages, and that means we try to reschedule all the tasks, which are the bubbles here. The partitions are now bubbles, so we start again from the very back, and each partition in the final stage, they will become a result task. And so we have, in this case, we have 3 result tasks, and now we go also back through the execution chain and schedule other tasks. Now we call submit stage on the last one, but we see that it has unevaluated, unresolved parents, so we have to submit those stages first. So we actually go recursively through the plan and submit stages, and submitting a stage just means to schedule the tasks using a task scheduler. So that's actually how Spark executes stuff. Now I push back again, sorry. So I think that should be clear now, right? Now we haven't covered one question yet. So with the last picture, I think it was pretty obvious how MapReduce and Spark goes together. I mean, every stage was a map task, pipelining together map functionality, which we can apply on our data independently. And then we always have to redistribute to apply the next stage, right? So between every two stages, we always have a shuffle dependency. So we need to exchange data. And the question is that we haven't covered yet is, how does Spark actually get data through a shuffle dependency? And also here it's very similar to MapReduce, but Spark actually implements 3 shuffle algorithms. So the first one, so we have a shuffle manager, which basically selects the shuffle type for us, and it's instantiated on the worker. So we have one fallback extraction, which is called sort shuffle writer, and which is basically the same as in MapReduce. So what it does is it has an in-memory buffer, which is a map or a map if we have a combiner. Like a combine is we combine intermediate results on the map side already. So we have that in-memory buffer, which is specifiable over configuration. Now which is partitioned also, and will be sort and also provides a sort function. So what happens during a shuffle is the map paths, they will be executed and produce intermediate results. Those intermediate results are put into a buffer, and once some memory pressure occurs, which is defined like configurable again, once the pressure is high enough, I don't know, 70%, I think, those buffers will be spilled to disk, and they will be sorted before, like in MapReduce, right? And once we're done, we load again all those build files, and we merge them together to build one final file, which is the map output file then. And then we report it to the map output tracker and so on. So the problem here is we have a lot of overhead doing serialization, deserialization, and we always have that in-memory buffer, which is very inconvenient to use, right? So that's why it's the fallback. That's why it's the fallback implementation. So they've come up with some better implementation. Then there's another implementation called the bypass merge sort shuffle writer, which bypasses the sorting. And it's used once we have a map site combined, because then we only produce one single result for every key, because we're combining all the keys on the map site. So we don't need to sort by key, but we still need to partition. And it gets used if we have defined a map site combine and an aggregation function. And we only have a small number of partitions, and the default is 200, because that implementation, it actually opens one file for every partition and writes the records directly to a file before it finally merges the files without sorting them. The merging is done on partition basis. Yeah, and the problem here is, of course, we have all those files open. If it's 1,000 or 1 million per worker, that's of course a problem. And we also have, for each partition, we have that we take aside some buffer size, which is configurable as well. So we have num partitions, so the number of partitions times the output buffer size, which takes a lot of memory away from computation. Yes, so that's actually the drawbacks. So basically, it skips sort, which is the upside. But we have so many open files, and we require a lot of memory. And then there's the newest implementation, which is pretty advanced. So it uses some serialized sort, but only if the serializer we are using supports to sort data that has been serialized and written to disk before. And if we don't have an aggregation, because if we have an aggregation, we would use the bypass merge sort right there. So what the unsafe shuffle writer does is it serializes a key value pair and puts it directly to disk. And it keeps in memory only an array of long values, like of 64 byte bit values, which are composed of the partition ID of the tuple and a pointer to where it's in memory already serialized, on disk already serialized. And then once we have to spill, we sort only that array consisting of some long. So we don't have to keep the actual data in the memory. We only keep those long values in memory, so we can operate way longer until we have to spill because the data is just actually on disk already. And finally, it also merges those spilled files, also using the same on disk operations used by provided by the unsafe library. So, and the upside is of course that we have low memory pressure. All right, that's been some details on shuffling, right? So to wrap things up, I don't know how long it's been now. Parallelism in Spark is achieved by data decomposition, applying the functionality independently of all others on a small set of data, then redistributing and reapplying another function. We have a partitioning function which specifies the redistribution, and Spark actually breaks down all our workload that we committed in exactly that model. Like we have the map task, and we have a shuffle, and then we have another map task. So there are two processes that could be responsible for performance issues. On the one hand, if the execution of the function goes wrong, we have a straggler task. So one task takes way longer than all the others during the execution, during the map phase of in a stage, right? And the second potential performance bottleneck is the redistribution itself, like the shuffle. If the shuffle takes very long, that's the second source of performance bottleneck. When it comes to straggler, data characteristics, so either our data has already that skew, like if we think of the word count from before, we have one book which has 5 million pages, and all the others are just single pages, then the one worker who has to process the one very large book will naturally take much longer. So to tackling this, we would need to do some sophisticated process. We need to measure what happens to see what's really going on, and then we would have to split our book, for example. So we would need to add some randomness to our data. Or data skew is produced by some poor partitioning. If we think of the book example again, if we put 5 very large books into one partition and another partition has just one paper, then we have a poor partitioning leading to a data skew again, because the one worker has to process all the large books, right? Or data skew is produced by bad design, which is kind of related to bad partitioning, but we could actually collect, once we use objects, once we build some domain model and we collect large amounts of data into objects, which are not scalable but have to be handled with one task, and we don't even know how long our list will be, for example, it could be possible that we create our data skew ourselves. So it would be better to write a more scalable function, like some aggregation function on really atomic objects. Okay, straggler test could also be a result of bad hardware. For example, one of our nodes is super slow. It's super slow writing to disk, or it's super slow over the network. it has a bad CPU, for example. So that's basically the reasons why we could have straggler tasks. When it comes to shuffle, most of the time it's a poor shuffle performance is caused by shuffling around too much data in the end, which is also a result of bad design. I think again that's especially in the core API when we use that. Or if we could use a combiner, for example, which is related to bad design or shuffling too much data. Or if the wrong shuffle algorithm is used in the end. Like you have control over some parameters that I mentioned before when we looked at the shuffle algorithms. So you really need to track what's happening in order to monitor and debug your application. And that's actually the point that I want to make. If you want to debug and monitor your performance and you really want to improve your performance, you really need to measure and try to get insight what's going on. And that's also what I said before. But you need to ask the right questions and you need to understand what's really happening and what those numbers are going to tell you to draw the right conclusion and actually to fix the problem that you're facing. So we didn't talk too much about how we could do that, how we could measure that. But I think each of those topics could, I think, fill another talk. I hope, I mean, any one of you or every one of you could at least take away something. And yes, once again, my name is Philip, and I'm not only happy to answer any questions that you might have, but also if you have any kind of feedback for me on that talk, if it was helpful for you or not, or about the content, if you would like to see, or if you were interested in something else, I'm very happy to take that one. And yes, hopefully I get some feedback and hopefully enjoy the talk. Thanks for your attention. Yes, are there any questions? Yes, please.
So the first slide that you showed us, with that slide you mentioned the garbage collection problem.
Yeah.
So in your experience, two things. One, what was the best garbage collector and why? If you had a chance to compare and use, leverage several of them, GC1 or other ones, and two, what approaches did you take in order to fix that type of problem?
Yeah, I would like to answer the second question first, because it answers the first one actually. Actually, that was pretty simple, right? So we had a huge. You kind of see the used memory, but it basically uses 100%. And what we were seeing was basically they were trying to cache data all the time, and kept it, so they didn't actually track it, right? So actually they were just using up all the memory, so it wouldn't have made any difference which garbage collector you've used. Because they were really keeping all that, so it really had to copy all the data all the time. Then they're recaching something, and then they would have to put it away again, and it was just too much caching. And that was very easy to identify, and that's why I mentioned it here. But the point is, they at some different places they had some really good results caching, and it also speeded up things here before it went too much. So what you need to do is you need to measure how large is the input data sets, how much memory do you need for that in order to apply your algorithm in the way that you have developed it, because it runs on different machines, it runs differently, right? Because if we had twice the memory of that machine, it would have run just very fast because it caches data all the time, right?
Okay, so besides memory and caching, did you find yourself useful techniques in changing the actual data model, so the data types that you were processing, and do you find any evidence in changing data model which would imply decreasing GC time?
And decreasing GC time.
Changing the actual data model.
Basically not. I mean, we had some model changes towards reducing stragglers and data stream, for example, because just the problem was poorly modeled in terms of a parallel or a scalable program. But despite from them, we didn't have any like too many GC problems additional to that. So it was slightly, sometimes was slightly above 10% or something, but nothing that you would worry about. There were many other problems that would have to be tackled first. Because it's a very detailed question, right? So I think that applies to many problems. Usually you have some other design issues that you could tackle first before you go really into details and see, like at JVM level, where it can do better.
Other questions? Okay. So
you again?
I have one.
Okay, good.
Sure.
So, yeah, because the community is great, guidelines are great, but in my experience, what mattered the most in writing actually really scalable Spark jobs was experience. So since I assume you had this kind of experience in writing out Spark jobs or putting your hands on to improve Spark jobs and make them scalable, how often did it happen to you that you had to write your own partitioners to get balanced data, so not skewed data?
Yeah. Actually, I did it. True. However, the point that I wanted to make is you have to know when it's going wrong, right? So, and we saw ourselves, which collected actually a list of very many objects. Like that's bad. That's very bad design again, right? So you build a list, you build the domain object, which has a very long list of other objects, and it was collected, and we just got rid of it by using a combiner function. But actually, it got faster, but you cannot get rid of that data skew yourself without adding some randomness, right? But the point that I wanted to make is you really have to know if it happens, then you can think of different ways to implement it. But it's not necessarily has to be a different partition. But there are approaches which are pretty sophisticated, which measure with aggregators on the workers. So they give you an overview of how your data looks like, and they repartition differently. If you have one very large partition, then they partition some very small partitions together to make up the same. So it really tries to distribute the data equally among the partitions. There are some approaches about that.
You have another one?
I had many other ones, but leave me up to the
Yeah, sure.
Okay, so thank you again.
Yeah, thanks.
Okay. So I can give the talk in English or Italian. What do you prefer? My English is not as good as his English, but So last time we talked about HBase and how HBase works, the under the hood underlying technology that's on HBase, and we saw also how MapReduce and Spark jobs can interoperate with HBase, and that was the key to understand what we are trying to present today. So today I'm going to present pattern to access HBase data from both Spark jobs and web applications, and take the most out of the technology in order to both process it massively and punctually, so record by record from a web application that has different response times than a batch job, has different memory constraints, and it's different execution context. So we stumbled upon this use case a client gave us. He wanted an inter-process communication area, so usually you go with a staging area where you put data from one batch job, data that's the result of a batch job and it's the input of another batch job. That had to be persistent, so in case of machine failures it doesn't get lost, but also they wanted it to be queryable from a user interface with a lot of different access patterns. So there wasn't only one access pattern, but the user might want from the web interface to filter on some fields or other fields, and that was the problem. So the processes that need to exchange data were Spark processes with dozens of cores, and the most part of that data is consumed by those jobs. So like 99% of data must be read massively from Spark executors and processed massively, and so we wanted to have a high throughput of those jobs, but also we wanted to be able to access from the web interface, and we had service level agreements on the response time of those interfaces. So we needed to access that data really fast, like less than a second to visualize data. And so the easiest way to implement it is to apply an anti-pattern that's databases IPC. And what you usually do in this case, and actually what you shouldn't be doing because it's an anti-pattern, is just store records in a database and read it from your batch processes, and when you have processed them, you just mark them or delete them. And it has some pros because it's a database, it's a table on a database, so it's queryable. You can have indexes on them, so if you have multiple columns you want to filter on them, you can do it easily. But you have also downsides. So indexes are slow to update. The pattern to access all the data in the database is not easily parallelizable for RDBMS, and also it's not what RDBMS is built for. Also, usually RDBMS are not horizontally scalable. So when your data reaches some point, you won't be able to serve it with a bigger machine because there's no bigger machine, and you won't be able to access your data at all. So that's how databases IPC could work. You just have records, you have a flag, you read all the not processed, not flagged data, and then after you have done some processing, you can mark all the records as processed and or delete them, whether you like to keep the history or not. Another approach might have been using files. Actually, Parquet files, that is a common data format for data on Hadoop clusters. They have also pros that kind of the opposite of the database's IPC pattern. That's one is that is easily queryable from Hive and Impala. Hive and Impala are just SQL interfaces to MapReduce-like jobs. Also, being files and being them on HDFS or on a storage that parallel disabled means that you can read the whole file with a high throughput. Also, Bright is parallel disabled for the same reason. But small queries, so the one that we wanted to do from a web interface, would have been really slow. And also, you cannot update files. You might reread them, change some records, create a new file, delete the original file. So it wasn't easy to update data. That was also a requirement. So we thought that actually HBase is a database, so you can query it with fast response times if you have the key, and actually stores its data on HDFS, so might be a good fit. Its pros are that it's horizontally. You do not know the row key of your data. You're going to scan the whole table. That won't be efficient at all, and you're not meeting the requirements. Also, if you do full scans, the region servers might hang for a long time serving your request because it's a big request. You're requesting all the data in the table, and that way region servers won't serve other RPCs from different clients. Also, actually delete and put on a HBase table are kind of the same thing because you're just appending a record to files, and even though you delete the data, you're actually creating more data on top of your original data, and so performance will drop because you'll have to scan bigger and bigger files, and then you will hit compaction, both minor or major, that last time we saw how they work. And those compactions are heavy and will slow down your HBase and your database. And so you will have performance ups and downs because sometimes the compaction will be running and your data will be a lot slower to serve. So we thought we could do better, and we can think that data actually is on HDFS, so we might access directly data from HDFS. And we saw last time that if we operate on HBase snapshots, we can actually read directly H files. So read data from HDFS, do not make region server hang on our requests. And so we had added that pro to the list of pros. Another pro is that it's possible to delete entire snapshots. So we don't have to issue a delete for each record we want to delete and we have processed, but we can take an entire snapshot and throw it away or store it somewhere else. We still have one problem, and the problem is that usually on HBase you can think as hard as you can to create a model that fits your needs, but you won't be able to access the data in a lot of different ways. You have to know at least a part of the row key, and given the access patterns that the client gave us, it was not feasible to fit all the data in the row key and access it in a smart and easy way. So if you didn't know the key, the query would have been really slow and make the region server hang again, and we are going back to the original problem. So we put in another component. That component is Solr, and Solr works as an indexer, and so makes possible to query it, and given a field that is not the row key, interrogate its index and give us the row key, which we can use to query HBase and get the data out of it. Also, with the thanks to NG Data, that's company that developed actually didn't develop but put together some tools. It's possible to do near real-time indexing of HBase records, reading directly from the write-ahead log of HBase, and index those data into Solr. So Solr is kind of new component. We never talked about it, and it's a standalone full search server. It uses Lucene in its backend, and actually what it does is offer a HTTP REST interface over Apache Lucene. That's just a library for indexing, and that's what it does. You give him data, and it indexes it, so you can look up on those indexes and get back the keys that what we wanted. So that's why we used it, and how we used it. We built indexes with Solr. It is another pro of Solr is that it's horizontally scalable, so you can add more machines to your cluster, and you will be partitioning your data into more machines, so the indexes will be distributed in more machines. Also, as I said, NG Data developed the near real-time and batch indexing from HBase tables to Solr. So we have leveraged it to index data. Also, we could store, and we have stored indexes on HDFS. This is actually nothing impressive, but it's useful because we have control over the data. We don't have to look up on workers. We know where the data is, and we can monitor when it becomes more or decreases for some reason. So the component that connects HBase and Solr, it's called HBase Daily Indexer. It's possible to build indexes both in a batch fashion, so using a MapReduce job, or near real time through asynchronous indexing. This means that even though you're building an index on every HBase put, you're not actually blocking HBase put and limiting its throughput because of these indexes, because it's done asynchronously. So it's eventually consistent. It's not the best, but actually it serves our purpose. So how the indexer, the batch indexer works. You have a region server that receive that contain your data, and then you have MapReduce mappers that read directly from HBase the data. Inside the mapper, there's this Morphline pipeline. That's Morphline. It's an SDK to do declarative ETL, extract transform load. So you have some logic that takes HBase data and maps it to Solar records. And then data gets exchanged based upon its key, because if you have multiple Solar servers, you'll have your data shared. And so each server will serve a partition of the data. And so you have to create different indexes for different Solar servers. And then the MapReduce job puts that data into HDFS, and Solar server are instructed to go read that data and serve those indexes. This is not so fantastic. It's the batch offline way of doing it. The really cool thing is that they also built a near real-time version of it. That's a lot more sophisticated in my opinion, but you will get actually the same result but in real time. So what happens when a region server gets an RPC with some put or delete actions on data, that the put and delete will be both stored in a mem store, so in memory, and on a write-ahead log, so that if the node goes down, you will have the copy of the data and the action that happened on it on the write-ahead log. The write-ahead log is linked to a replication source if you enable it, and the HBase indexer that ngData built is a listener of that replication source. So every time you manipulate with Morphline SDK to create Solar records, and these Solar records are insert into Solar indexes that actually are baked by HDFS files, so after the data is eventually stored into HDFS. So how the whole thing works. As you can see, here we have all the actors that I've mentioned before. You have HBase with this write-ahead log, memstore, and replication source inside. You have the HBase indexer that I've just mentioned. You have Solar. Then you have HDFS on the bottom of the screen. And you have both producers and consumers. Both producers and consumers are distributed applications. So one producer might consist of multiple nodes and multiple processes that write concurrently data or write data concurrently on HBase. And you have usually one consumer. And also that one consumer is a distributed application. So what happens when puts are issued to HBase? They both go to write-ahead log and memstore. Then from write-ahead log, data goes to the replication source that triggers HBase indexer that inserts data into Solar. And actually you do a lot of puts, so the memstore gets full and it flushes. It flushes down into an H file. That's the file that are used from HBase to store data. And you have another producer, you do another bunch of puts, and eventually the memstore will be flushed to another H file. And then comes the consumer. The consumer wants to read the data, but doesn't want to read the data using remote procedure calls, because it will hang the HBase region server. And so it talks to the HBase master that's not actually serving data, but just coordinating the whole HBase cluster, and will do a couple of operations. The first one is to disable the table. This is needed because if you take a snapshot of the data without disabling the table, you won't get consistent snapshots. And this will lead to record loss, and doesn't feel good at all when you lose 3 records out of 10 millions, because you won't be able to find that out until something really bad happens. So you have to disable the table, take a snapshot of the table. Taking a snapshot of a table on HBase just lists the files, the H files that are backing the table, and write them somewhere. Because those files are not mutable. They are immutable. They won't be modified by anyone. At least they can be removed only if no one is pointing at them. But you have just took a snapshot, so they won't be deleted. And then you can re-enable the table. So you will end up with a 5 to 10 second time span where your table is disabled. That is not a problem for producers, neither for other people that might interact with that table, because the region server will only queue the requests, and after those 10 seconds the request will be served. So there won't be any failure, just the request will be served lately. You have some time that you have to wait before you get the response, but you won't hit the timeout. So for readers or for writers, they will experience some lack of performance for those 10 seconds, but nothing will fail unless the whole process of enable snapshot and disable snapshot and enable will take more than that timeout that usually is a minute. So the consumer actually does these 3 actions and then knows which are the files that are pointed by our snapshot, and we'll directly read those files without operating with the region servers. So it will do some processing. That processing might take some time. And so in the meanwhile, another producer might come and write data. And that's perfectly fine, because even if it will make the memstore full and the memstore will have to flash on a new H file, we won't be reading that data. So we will be consistent with our snapshot. And so after our processing is done, we can actually delete data. So delete directly H files. We're not putting new delete records on top of the old records, but we're just deleting physically the files from HDFS. If we want to be more conservative and keep data around for some reason, we can just move them. And actually, we also have to remove the records that we've removed from HBase. We have to remove also the index entries for those records. In the meantime, there might be someone from the web interface that is querying Solr, but since we know that Solr is eventually consistent, we don't show up results to the user. We don't show up intermediate results to the user. So even if the index is not in sync with the database, we will drop all the records that are not both present in the index and the database. And if the index has less record than the database, they won't show, but from the user perspective, it won't be bad because he doesn't know what he's looking for. Usually he wants to rank data on some function, and so he doesn't expect a specific record to find, and you won't feel bad if something doesn't show up on the first try. So that's the whole toy and how the toy works. And we did some experiments on it before actually building something upon it. So we experiment experimented it with a small Hadoop cluster with 3 nodes, 32 gigabytes of RAM each node, 4 cores, and SSDs for disks. The software was configured that way, so each node had a region server, plus one was also serving as a master. We had 2 Lily indexer and 2 Solar Cloud instances. Actually, those 4 processes were running on the worker that wasn't running the master, so it would have been a little bit more balanced. And then we had the YARN to run Spark applications. And about the test data, our client said that those hires won't store more than 12 million, about 10 million records, so we tried with 12. The data was at a schema of 30 fields, 20 of them are nested, and we were creating and we were issuing query only on 8 of those indexed fields. 6 of them were strings, 2 were integers, so we could do equality search on strings and between filters on integers. So the whole data weighted about 6 gigabytes on Parquet format, and almost the same as other records after they have been inserted into HBase, so quite the same dimension. And also, when we built the full index of 6 gigabytes of data, it took up to 1 gigabytes of space on Solar. Solution based on Parquet files. That was the other option we might wanted to go through. And so write is a lot. It's like 3 times slower on HBase. For the HBase part only, and then like 5 times slower than Parquet files for indexing the data. Also, it was using a lot more CPU because indexing is costly. But you don't end up with an order of magnitude of difference. So 3 times is not 10 or 100 times. Also, for massive read, we got even better results because reading data from HBase took like 30%, 50% more than reading data from Parquet. That's probably the fastest way to read data from HDFS. And the delete times were comparable. Actually, they are the same because we're just deleting files from HDFS, so it's not a costly operation. Then we run some benchmark in order to see if the area could have been queried simultaneously by a lot of users, and we saw that how many records you're going to retrieve from Solar is going to affect the query the most. So we tried first with limit 100 records, and then with 1,000 records for limit. And so we try with different configurations of the benchmark. It's difficult to read, but on the bottom there are 4, 8, 16, and 23. Those are threads. And the different queries are, so the different colors of the lines are different queries. So we see that the Solar plus HBase scales really well, since even though you're making the double of requests, the response times were actually kind of linear. So we all have a response time even when 23 different threads are issuing queries continuously. You get response time in less than 150 milliseconds. So in my opinion, it's a good throughput, since operators are not gonna click like 100 times in a second, so it might work. and the results are worse on using a limit 1000 query, because Solar was the bottleneck of that in that case, since it uses term frequency inverse document frequencies that performs kind of badly when you have a small number of different terms, and so you build really big files with a lot of so you end up having big files with those indexes, and so you end up with slower response times. But actually, for us, it wasn't a problem, since we were displaying that data on a dashboard, and almost no one wants to display 100 records, 1000 records altogether, because it doesn't make sense on a table for a human to read 1000 records. So this case with 100 or 200 is more near to the reality of the application. So we did some experiments on Parquet 2 in order to compare the result. So for Hive, Hive actually is a SQL layer on top of HDFS and uses MapReduce as its execution engine. And so every time you issue a query, MapReduce job gets started and executed. And that takes a lot of time only to initialize. So it takes about 35 seconds to perform a single query from a single user. So it wasn't completely out of scale. We also tried with Impala. That actually does the same thing as Hive, but it's written in C++, doesn't start MapReduce jobs, but has daemons that are always running, and therefore doesn't have all the initialization overhead of Hive. And actually it works a lot faster than Hive, because you get queries executed in 200 milliseconds, but only stimulating it with 4 threads, so simulating 4 different operators from the user interface led to exception in collecting the results, and so it doesn't work that well for concurrent load. Actually, because it has to scan the whole Parquet file every time you issue a query, or you can push down some filters, but it doesn't happen so much on our queries. And also because of that, you get a lot more I/O than on the than compared to actually querying both Solar and HBase. Okay, so what are the bad sides, the drawbacks of our solution? There is a delta t time where index and database are out of sync, and so that might lead to inconsistencies when you're trying to query the data. Also, in order to consume messages, you have to disable the table for a small amount of time, and that can lower the throughput of writers and other consumers. Also, you introduce a new component, and that component actually does a really good job because it creates indexes so you can do different queries on it, but it becomes the bottleneck of the system. But the good thing is that you can scale it independently from all the other components. So if you find out that is a problem for you, the response time of Solar, you can just put more instances of it and parallelize the indexing process. And also, if you have a low variability of a field, term frequency, inverted document frequency doesn't perform very well. So those indexes that are built upon fields that don't vary that much don't perform as good as the other ones. But you can think about different ways to to tackle this problem on the HBase side if you know exactly what the variability is. The pros are that it actually works for our use case. You get all the queries in less than 200 milliseconds. That was our goal. The queue-like read, so when you have to read the whole table, is only 50% slower than Parquet, so it's comparable to it in those terms. The deletes you're issuing are compaction-free, so actually you won't have the time spans where HBase does compaction, because you're actually disabling it and doing compaction yourself because you're deleting the files. And also massive write is 3 times slower than Parquet. That's not that much. Met our requirements, and you can do updates. I think that you cannot do on files. And so, yeah, I think that's all. We've shown that it's possible to create that inter-processor communication area on top of HBase that is both readable and writable from batch processes and from web interfaces, so with really different data volumes. It is queryable with sub-second response times, and you can actually, thanks to Solr, apply a condition on multiple columns, so you end up with files. That's kind of the fastest way to read and write data from Spark in a persistent way. And it's compaction free for the nth time. And so that's all. It's a bit dark, so we go back or we fall asleep. And that's all. If you have any questions, I have a slide with questions on it, but if I put it, we're going to sleep, so maybe I'll go back. Okay, so this time I took only 8 minutes more than what I thought, so I'm coming better at this. And yeah, if you don't have any questions, okay.
When does the Solr index get updated after the snapshot?
So when you delete the snapshot, you first delete the snapshot here, and you're deleting the H files, and then you issue the delete query to Solr. And if you are smart and generate IDs in a monotonically increasing way, you are able to perform that the delete in about less than a second. So it won't be perceived from the user that you actually have a skew between the database and the Solr. Actually, also because in your application logic, client-side application logic, you're first querying Solr, getting the keys, and then querying HBase. So if you get more keys than what actually are on HBase, you know that's because Solr is out of sync. It just won't show those records, and reissue the query and get another 100 keys and use those one to fill the space. So, and actually that happens in a small fraction, in a small interval. So you have to be really unlucky to hit those moments when the data is not aligned. In fact, we show that 12 million records get inserted in 6 minutes, but we also said that 10 million records is the maximum size of that area. So it was right after this. Okay, so we ended up with 10 minutes of indexing because we inserted all the data in a big batch, but usually you write like 1 million of records or a couple of thousand, 100,000 of records at a time, and so that delta between HBase write and Solr indexing will be much lower. And so it would be hard to just hit the query button in between it.
Who does trigger the
It's the Spark job. Yeah. If you are using near real-time indexing, it does delete data by itself, because delete, like insert, are like put, so they go through the wall and then to the replication source, and then the indexer can delete the data from Solr, but we are bypassing the write-ahead log and the memstore, and that's why we are that fast to delete data. And so it doesn't work automatically. So it's the consumer that actually deletes the data. Yeah, I forgot an arrow pointing from consumer too.
Because when you re-enable the table, HBase realizes that some snapshot files have been missing, but the indexer does not.
Yeah, exactly. So fun fact is that if you just delete data from, if you just delete files from HDFS that are baking a table, HBase doesn't have any problem about it. It just goes through the memstore. If you cannot find the record you're looking for, it looks at its file list and then tries to open those files in some order, and if one file is missing, it issues a warn and goes ahead. So it's perfectly fine to delete the H files because you won't bother about it, and that's why the solution kind of works. If it has some problems about file being deleted while it's up, it wouldn't work at all.
I think that a very nice thing about this solution also is that you can actually rebuild the index offline, so you can leverage both the purchasing of the real-time one and the batch one. So in your production system, you can have the real-time asynchronous indexing. But if afterwards you have to, do migration stuff, re-importing your data, you can actually rebuild the index.
Yeah. Actually, we tried that solution too, because you might want to compact the index or do that kind of stuff overnight because users won't be there. And so you can drop the whole index and rebuild it on the fresh data. And it's actually the same components doing the same stuff, so you will end up with the same index. But since you're doing it in a batch way, you might end up with better file compressed files, while when you're writing data live, you might fill buffers and so create smaller files that end up eating your performances. Okay. If no one has more questions, we can wrap up. So actually, the meetup is organized and organized by Agile Lab, the company where I work, and we are actually looking for computer scientists, computer science engineer, big data engineers, and our core business is actually big data engineering. Also not some, but I don't practically do it, so it goes in second. It's not what I'm doing, so I actually tend to forget it. But we also do machine learning and artificial intelligence and that kind of stuff. So if you're interested in working in an agile company, we're here. We organize Meetup every two months, and you can hit us on our website or through email or even physical. We're here. So thank you very much for everyone that came here. Thank you to Philip again to have spoken for us, and we can go ahead with the networking and appetizer and eat something because I'm really hungry. Thank you.